Okay, could you confirm that you can see it correctly?
Yes, looks good. Thank you.
Wonderful, wonderful. All right, well, thank you for having me and thank you for the introduction. We've been planning out this meeting for a little while, and then there's been a lot of delays. So we talked about doing it a few months ago and finally getting it done today. So I'm pleased to be here. And I would like to spend the time here talking about some projects at MBARI around wave energy harvesting and energy harvesting in general for enabling persistent presence of oceanographic instrumentation in the ocean. I think what we'll do here is I'm going to give a little introduction to MBARI so everybody understands a little bit of the context of why this is sort of the type of project we're interested in and activity we're interested in. Then I'm going to talk about some specifics about our wave energy system and application of the last couple of years that we've been doing, and then finally a third sort of section on a particular project we have where we're trying to make that hardware, which is deployed in Monterey Bay, available to other researchers sort of in the control systems, wave energy, marine energy harvesting topic area. So that's the plan here. So starting off, the Monterey Bay Aquarium Research Institute, MBARI, is located in Moss Landing. I don't know if you can see my little pointer here, but in the left picture is Monterey Bay on the central coast of California. And our institute is located right at the top of that submarine canyon that comes up right to our back door. And where that canyon comes into the very inner part of Monterey Bay is where our institute is and where I'm sitting now. And the picture on the right is our institute, these 3 or 4 buildings and research ships across the street. And this is a privately funded oceanographic institute founded and funded by the David and Lucille Packard Foundation. And really a core tenet of the place is engineering development in concert with science and operations. So there's 3 main groups of MBARI: a science group with chemists, biogeochemists, biologists, geologists, that sort of thing. And then an engineering group, which is about a third of the institute, which has a mechanical engineer, software engineer, different types of research and development engineers. And then an operations group, which operates 2 regional research ships and a lot of autonomous underwater vehicles and that sort of thing. And the whole group really is working together as peers to develop equipment and do scientific research and understand the ocean. And that's the goal and plan of the place. And it's quite a unique arrangement that allows us to kind of do a little bit longer term technology developments because of the funding arrangement. So that's that. I guess I will add that this canyon here is quite deep off Monterey, off Moss Landing. So you don't have to go too far until you're in a couple thousand meters of water. Like in a day, you can get into pretty deep water. So that's in contrast to some other oceanographic institutions, which you have to go a little further. So really, there's a lot of emphasis on deep water work and benthic ecology, and that sort of thing is a core part of what happens at MBARI. MBARI engineering really does a lot of autonomous underwater vehicle work. Here's some pictures. In the upper left is a fleet of a 12-inch diameter, long-range autonomous underwater vehicle. Those are developed and sort of used at MBARI. In the middle picture, there's a larger, sort of older style, Dorado style, 21-inch vehicle. There's on a ship getting ready to go, and you can see that there's cameras and lights on the front of that. So that's being used for biodiversity transects. Picture on the upper right is one of our research ships with a ROV in the orange there. That's the ROV Ventana, which is used on a pretty regular basis. And then in the foreground is a autonomous underwater vehicle developed in concert with Woods Hole called the Mesabot, so a hovering vehicle, track fish and such. Lower left is an interesting robotics platform, which is called the benthic rover, deep water again, 4,000 meters or so. And that platform, it spends about most of its time at sea. It spent about 8 or 9 years on the ocean floor, coming up once a year to have its battery changed, doing benthic respirometry experiments. And batteries are a theme of the talk here. And the reason that it was able to go an entire year between recoveries is that the use of the system is very duty cycled. It wakes up every couple of days and makes a new measurement. And that allows the energy stored in the system to be stretched out over an entire year. And the pictures on the lower right are some instrumentation and another picture of the 12-inch diameter LREV. Most of it is I like the picture. That's in our test tank at MBARI, where it's only one vehicle, but the reflection is mirroring across the surface. Looking up underneath, you can sort of see the undersurface of our test tank. but the vehicle itself in that configuration has a camera in the front with a ton of light. So that's vehicle has a lot of different payloads for the nose, and that's one example. So I think the theme here, a lot of MBARI engineering is really centered around persistent presence and extending instrumentation into the ocean for extended periods of time. If you draw a box, MBARI engineering does a lot of different projects, but if you draw a box, there's a lot of them in that sort of area. So that's kind of termed persistent presence, and that's a goal. I think a goal is to continue to develop technology to extend the timeframes that this equipment can be present. And you need a few things to do that. One is vehicles, underwater vehicles. Capability and reliability are keys there. Reliability being a big one once you start talking about vehicles being out for extended periods of time. Autonomy, the more vehicles you put in the water, the more time you spend sort of shepherding them around, so they need to have some autonomy to kind of take care of themselves a little bit. Instrumentation is critically important. And then energy is bold here in this picture. This is a lot of what I'm going to talk about. If you're starting to talk about having things out for more than a day at a time or a week at a time, you need to resupply energy. And then communications are important as well, and that kind of comes along with energy in some way. So options for energy, you have kind of really two. You can bring energy along in batteries, or you can collect it from the environment once you're there. And my graph on the right is a little bit fanciful. One I made that illustrates that, you can argue about the metric here, but the illustration here is that if you have a fixed amount of energy in the vehicle, the longer your deployment duration is, the amount of energy you have or power that you can expend at any given time drops in this sort of terrible 1/time relationship. So once you're out at 6 months or so, if you only have, like that benthic rover, if you only have a fixed amount of batteries, you really need to duty cycle the system back quite a bit. Energy harvesting system, solar, wind system in gray, or a wave energy system in red, has a different characteristic in that, the principle, the value doesn't go down over time. It just sits there and keeps collecting energy. The metrics, like I say, watts per kilogram, these are kind of based on some estimates. But I think, the illustration here is that really, if you just need to go out for a week or two, you shouldn't really be messing around with energy harvesting. You should just load it up with batteries and go. But once you start talking about 3 to 6 month deployment, if you want to have capability in that vehicle, you're going to need to find some energy in the environment. So to that end, a project that MBARI has been working on for quite some time is a prototype research type wave energy converter. And this is a simple point absorber. The illustration on the left sort of shows what's going on. The buoys following the surface of the wave. And then down below, there's anti-reaction mass, anti-heave plate or shape. And then that creates a differential motion between the buoy and the plate, which represents energy. And then in between those, there's in this case, an electrohydraulic power takeoff device, which converts that force and speed in the relative motion into electricity and stores it on the battery. It's a pretty big system. It's not to scale there. That heave cone sits at about a depth of about 100 feet. But the power takeoff device itself is pretty long at 7 or 8 meters. So maybe 7 or 8 meters. And then the picture on the right is the device going out to sea. So it gives an idea of the size and scope of this thing and that kind of thing. So this device is comparable in terms of surface expression to a solar power buoy. So the picture on the left is a solar power buoy that MBARI did some time ago that really tried to put as much energy, solar and wind energy capture on a platform of that size as we could. And that was about 5,000 pounds of mooring that collected about average 50 watts, maybe on a good month, 50 watts through solar and wind. And that's about what you can do on a platform of that size. And that isn't quite enough really to meet some of the goals. So once you go into wave power, the numbers for a similar size system, although a more complicated system and harder to deploy system, a similar size system, the power numbers start to look like an average power of 200 or 300 watts. So a 4 to 5 time increase in the amount of power from the sort of same amount of hardware, or approximately the same amount of hardware. So just to be clear, these are average powers, averaged over hours, weeks, months, and years in some sea conditions, and that's in Monterey Bay in this case. So in some conditions, like today, I'm looking out there and it's very calm and the numbers are lower. Today they'll probably be lower, and then tomorrow some wind chop will come in and they'll go up to 300 or 400 watts. So it sort of averages over time, that kind of number, 200 or 300 watts. So that, you know, I underlined the word oceanographic wave energy converter. Really, the emphasis here really is on power levels to power oceanographic instrumentation, not utility scale. And personally, I think that's a good place to put your energy in wave energy. Utility scale looks to me like pretty challenging. So the buoy is small, 10 foot in diameter, 200 watt average, as I said, and we do regular deployments of this system. This is actually a video, which I don't think I'm going to play because it often doesn't come off well on Zoom, but there's a dive. It's just one of our dive inspections. It's a neat video, but doesn't look like it's going to play very well. So this system is out pretty much every year for some time now, and this is this year's deployment. We went out at the end of March. This is hourly averages of a few different parameters, hourly mean power, and you can see the variability I was talking about, and hourly max power. So just because you're averaging 200 or 300 watts in an hour doesn't mean that's not coming in 7,000 watt gulps, you know. So we're going to talk a little bit more about that in a minute. And then the battery voltage is just a measure of state of charge. But if you, this data is all coming in. This is a close-up view of a particular hour of deployment. Piston position is measured, motor RPM, loads in the system, bus battery voltage, some ground faulty kind of stuff, and power generation. These are all these parameters plus quite a few others are being measured at 10 hertz and telemetered to shore. So these graphs are live and updated every hour or more often. So these are kind of pretty good monitoring of the system. And that comes from having the power to run the cell modem all the time and having a cell modem network nearby that we can connect to. So, okay, so some design features of the system, as I mentioned, is electrohydraulic power takeoff device, complicated device with some concerns about wear and longevity that we're sort of beating those problems down little by little. I think a key feature of the system is this heave cone and doors at the bottom that open and close. So you see those green doors at the bottom are articulated so they can open and close those 3 white triangle spaces. And this is a key part of this system. I'm going to talk about a little bit more about it in a second. The power electronics, as I said, the power comes in sort of big kilowatt gulps. So you need to have some specialized power electronics to convert that and store that energy in batteries. Talk a little bit more about that in a second. Onboard battery storage, then the buoy runs on 24 volts, has an Ethernet network on the buoy and a cell phone connection to shore. Linux control computer. Again, once you have a couple hundred watts to work with, you can put more significant computer infrastructure on the buoy than you might be used to in a weather buoy or something. The heave cone is a super interesting device in this system, and I think is key to the survivability and usability of this system. And this University of Washington and Oregon State people contributed to this design. They were a little bit of the inspiration for the upside down umbrella shape. We had just had a big old flat plate in our first iterations, and it did a lot of maple leafing and falling and instability. It wasn't very good, but Curtis Rush and others showed us from their experiments that if you kind of give the thing a little bit of natural dihedral, it behaves a lot more stably. And then we added this ability to open these doors in the middle, because as the weather comes, you kind of want a big anti-heave plate when it's calm and a small anti-heave plate when it's rough. And if you have a fixed device, I think that the dynamic range of the loads really gets extremely difficult to deal with. So this articulated doors that open and close are really, I think, a key feature of the survivability of the device over, you know, longer time frames and variable conditions. Similarly, as I mentioned, the power electronics are pretty specialized. This is a diagram of the system, a little bit more detail on that PTO. It's not shown horizontally, which is a little harder, but the rod here moves horizontally, and there's 2 chambers here. One is a hydraulic chamber with hydraulic oil in it, and then a pneumatic spring to provide a spring force. But the hydraulic side drives oil through a hydraulic motor, and it oscillates in both directions. So it's spinning from plus 3,000 or 4,000 or 5,000 RPM to 0 to minus 4,000 RPM, and then back to plus 4,000 RPM every 10 seconds, so, or 5 seconds or something. So That variable loading on the motor needs to be rectified and turned into a constant DC voltage to charge a battery. And it has to have a lot of sort of autonomous behaviors that it does the right thing in sort of weird edge cases. So that is a custom piece of hardware in this system. Here's an example of the powered gulp. This was I think this data was from yesterday when I added this graph to the slide, but it was averaging 329 watts over an hour. But that power comes in these gulps this is only 2 minutes of data, 120 seconds of data. And how many peaks are there? So every 10 seconds, you get this 3 to 7,000 watt influx of power that needs to be dealt with. So the power electronics that do that are pretty custom to this system and are shown at the top of this picture mounted on the back of the motor. So it's all pretty integrated system that converts that oscillating power into a constant 350 volts or so and drives that energy up into a battery on the buoy. So it's peak power, 10 kilowatt device, all to make an average of 300 watts. One of the many challenges of wave energy. So as an aside, this power electronics is actually right now also being integrated into a tidal turbine device at the University of Washington APL. So this is a device, cross-flow turbine, meant to power some electronics. And it's a very different system than the MBARI wave energy system in that it's slow. It's 100 RPM, and the dynamic range of the RPM is a little less, or a lot less. But even though it's slower, the power levels are similar, and the voltage constant of the motor was higher. So even though it's 60 times slower in RPM, the voltage constant of the motor was about 60 times higher, and the resulting system was still a good match for the same piece of electronics. So we've done a proof of concept integration test at University of Washington last year, and then we're planning an integration test with Chris Bassett and that group there in the fall of 2023. And to do that, this is a picture of the testing we did. There's Chris, actually. We did up there, and that's our power electronics sort of laid out on a prototyping plate, and then some ancillary equipment to make it all work in this environment. And the example of data on the right from that test, where we can measure the mechanical power going into the system and the electrical power coming out, and compute efficiencies and get a pretty good idea across the whole operating range of power versus RPM or torque versus RPM of how the system will perform. And currently that's being integrated into the end cap of that turbine. And we will be, I think later this year, going to be up there and testing it out again, and then making plans to do an at-sea deployment or continue to work in that direction. So it's exciting for us to have some of the work we did here, these custom electronics, find another use in another interesting project. Okay, so that's a little bit on the what the device is, how it works, and where it came from. And the question really is, what is 200 watts continuous use for? This is a problem. It's really unusual that you have buoy instrumentation that takes that kind of instrument, that accepts that kind of power. We sort of have 50 years of refining buoy-based instrumentation to use a couple of watts, not tens of watts. So we never really taxed the system of using all 200 watts. There is an exception that we've been fielding recently, the imaging flow cytobot and McLean Research HUI collaboration, which is ahead of myself, is a plankton microscope. And I'm going to give show some results of that interesting device in a minute, but it's about a 45 watt device. So we've been able, because of the availability of the power, to kind of run that 24/7 for months and months and months at a time and collect a lot of data. And they're writing papers now about the phytoplankton behaviors that they see with diurnal cycling and other changes in species, versus time. And then I think what we really believe is that the real reason to develop wave energy converters for oceanographic purposes is for autonomous vehicle recharge. In the beginning, I showed that we do a lot of autonomous vehicle development here, and that is our end goal, is to dock the vehicles to this system and recharge them. And the power levels are such that you could recharge a fleet of these things, but you do have to have the capability to dock the vehicle. And we have projects, I'm not going to spend a lot of time on that, but we do have projects related to that are moving forward pretty nicely. And this is a picture of the AUV. This is one of the LR AUVs that I showed in the first slide or second slide on the dock. And the dock in our case is a vertical rod and a latch arrangement. So the vehicle, this is looking up from the anchor. I know it's a difficult picture, but it's looking up from the anchor, taking a picture after the vehicle has sort of acquired the dock and latched on. And once it's in place there, through some cleverness and the use of a material called niobium, we transfer power across that rod without rigidly constraining the vehicle. So that's a relatively new development, and we are more and more deploying this type of dock in Monterey Bay. And we don't have immediate plans to connect it to the wave energy device. We have a couple other intermediary steps on the docking side, powering it with a solar device, or Mars, our cabled observatory, our seafloor cabled observatory. But in a year or so, we are working towards coupling this type of underwater vehicle dock to the wave energy buoy to allow, well, yeah, so we have somewhere to put the power, so we can charge up these vehicles and let them swim around. They're hungry, they take power. So. But the flow cytobot is a good story as well. This is the device on the left, and we've mounted it on our buoy. And as I said, it's about a 45-watt device and generates a little bit of data, about not enormous amounts, but enough, 190 gigabytes of images. Yeah, I should have a spec on here that says gigabytes per day. I'm sorry that I don't, but it seems like a lot of data. It's enough to be able to bring it in over the cell modem without taxing ourselves too much. But it is, a lot of data. It generates thousands of images every hour by pumping water through a flow cell and taking pictures and exciting the chlorophyll with a laser and that sort of thing. And here are some of the example pictures from any given, this is just from a given hour, 839 images from an hour. And there's these sort of gorgeous pictures of all this plankton. I'm not an expert or even close, really not even very knowledgeable about plankton. So can't tell you much about these, but I like looking at the pictures. But the thing you will see immediately is that there's a lot of pictures, and this is happening every hour. 1,000 of these pictures are coming ashore, and you can't really sit down and look at them. So it's just too much to do manually. So graduate student at Santa Cruz, University of California, Santa Cruz, named Patrick Daniel, has developed a machine classifier to use machine learning techniques trained on different images of plankton to kind of classify all these images. And I, again, don't know much how this works other than it seems to work pretty well. And net is that it takes these collections of pictures and turns them into histograms versus time of species. And that allows them then to do some science studies about, sort of what's happening in the bay here. Example in the next slide is this type of plankton blooming, and these are what they look like. These are just examples of the pictures. So you can see they're pretty identifiable. You can imagine a machine learner would be able to kind of recognize what this is. And here's an example of the quantity versus time of this. And they're asking questions of they see this bloom of the light pink color, but none of the other quantities are changing. So they're doing science studies about what that means exactly. Is this competition with the other diatoms? And you need to refer to Patrick Daniel if you have particular interest in this type of thing, because I'm using it here as an example of what we're using the power for, and it's not my area of expertise, but I do think it's been pretty interesting, and is in fact it's a part of a series of these flow cytobots that are deployed all up and down the California coast, sponsored by the state of California, looking for harmful algal blooms and water quality issues. And every one of them, almost every one of them, is on the shore, on a pier, because they take a couple hundred watts and an internet connection. There's one was placed on the mooring in Del Mar and duty cycled way down, because that's a small buoy with solar panel supplies. So they had to just take a few samples a day in order to only turn it on occasionally. But there's the one on our wave energy buoy here in Monterey Bay that is sort of a different animal in that it collects data all the time and radios at home. So I've been looking at time delay. Santa Cruz Wharf is just 15 miles away from where the wave energy buoy is located. So they'll see the same signal in both sensors and make some conclusion about the behavior of these blooms in the bay. And some of these are harmful algal blooms, so that they are interested in doing water quality warning for people that are going in the ocean. Although I'm not convinced they're going to keep the surfers out of the water no matter what's in there. But anyway, so that's the story on the, one example use of this device and the power that it's generating. I'm going to shift here a little bit and talk about some of the technical challenges of this device and the software efforts that we're working on in order to address those, or at least work on them or do some research. A big issue in wave energy is reliability and storm survivability. It's a bit of a ridiculous ask. If you put one of these devices out for a year, there's millions and millions and millions of wave cycles that go by, which translates into 1 to 2 million meters of linear travel of the RAM moving up and down through the seals. So there's a lot of very refined engineering to make that work and sort of stand up to these kinds of cycling. Wave energy is unique, not entirely unique, but almost entirely unique in engineering, where we're designing the thing for the maximum force. And that really gets problematic when you have an extreme event. And what I mean to say is the speed of the waves are the speed of the waves. So all we can do to make more power is to increase the forces. So like every other mooring in the world, we've designed to have a real stretchy rope going to the seafloor so that it moves around and doesn't have high peak loads. We're sort of driven towards engineering these systems for peak loads. And that's fine when it's calm, but then you get bigger waves and those peak loads get very, very difficult to deal with. So that's where the variable geometry heave cone comes into play to sort of curtail, at least reduce those extreme events a little bit. Now, when you talk about small scale wave energy, the system natural period of this device, just based on its size, and it's a little unavoidable, is short. It's about 2 to 3 second natural period. So it responds to higher frequency waves, wind chop, and that sort of thing. At best, it's even below that a little bit when you talk about its natural frequency. And there's a lot of work out there to address these issues through advanced control systems, which are reacting on a wave-by-wave basis or tuning the system otherwise to try to shift that natural period of the system through control systems. We do not, at the moment, do anything like that on our system. We take the simplest possible approach and apply a PTO force that's just simply proportional to the velocity of the RAM in the system. So it's really a linear damper. We can change the damping coefficient a little bit depending on conditions, but we don't have much control over that. There's an opportunity here to make a dramatic change in the amount of energy being captured through advanced control systems. And I think it's possible a lot of people in this audience are familiar with these ideas. But if you know what waves are, it does sometimes require that you know what waves are coming, but there are a lot of work in simulations, like shown on the graph on the right, that if you know which waves are coming and do some optimum control, you can maybe make 5 times the amount of power from a given device. Now, it does have a couple of requirements. You can see on the right that the red line, the power absorbed goes negative sometimes. So that means the system has to be able to return energy to the ocean at some parts of the wave cycle. So that's a requirement on the power electronics and control system. And the MBARI wave power electronics can do that. So there's no real hiccup there or hindrance other than efficiency. So, there's a lot of work done in simulation in this world in order to make this, a reality. Very little of this work has been done at sea or demonstrated at sea. And I think that drives us to our next topic here and our interest in using the system that we're deploying each year in Monterey Bay to provide opportunities to do some of that research on an at-sea device. Should we succeed at that, there's a lot of opportunities here to make the device smaller, impose stroke constraints, increase robustness, and increase energy capture. So this is a project that's been funded now for about 1.5 years by the Department of Energy. And it's a collaboration between MBARI and a company called Robotics to develop a software infrastructure on our existing buoy that is an API, basically, that would allow someone else to come along and write control code that can hear what's going on the buoy, how fast is the motor moving, all the data on the buoy, and then impose a control law on that. And so it's a little bit ambitious, but the fundamental goal is to make this MBARI wave energy converter that we're deploying on a regular basis available to outside control researchers to kind of try out or demonstrate concepts. So the approach that's being taken is to use ROS2, which is a robotics middleware, very popular in the robotics world, to provide that interface. And I'm not going to go a lot of detail on how that works. Some of you may or may not be interested. experience with ROS, but it is a middleware, a publish subscribe message passing middleware, such that our system is now out there publishing on in a predictable form all the data it knows about, the RPM of the motor, the load cell, all the data, all the telemetry that I showed in some of those graphs is published on the buoy computer network. And it also, the buoy is then able to respond to requests to change the loading of the system or a number of other sort of parameters in the system. This we feel is enabled by the sort of compute and control architecture of the system. So the way this system works is there's a buoy. I told you already, there's a buoy, power takeoff, and then a heave cone. Most of the critical function of the system are implemented in microcontrollers. There's 4 microcontrollers, one in the battery, one in the spring section, one in the power converter, and one in the heave cone that really do perform all the important features of the device. So if with no additional interference from the outside world, they will do the right thing, behave as it's working right now, and make power in a linear proportional law. On the buoy computer, there's also a Linux, on the buoy itself, there's a Linux computer that can override some of those behaviors. So the way this works is, and the graph on the right shows a cartoon here, the buoy Linux computer has a number of processes running on it. Some of those on the right are drivers to talk to the various microcontrollers. And then there's some processes of logging and short communication and oversight process. But really, it has the possibility to run a more advanced control algorithm than the system would implement by default and override the behavior of the microcontrollers. And that's what we are trying to enable people, ourselves or other researchers, to write on our buoy, our control algorithm that would run here and take control of the system and give messages to the microcontrollers to do different behavior. Now, the microcontrollers are smart enough to not do something damaging. So that's where we kind of have some confidence that we can do this and are kind of willing to open this up to other software engineers that aren't, quite as familiar with the system as we are. Of course, to do that, you need a simulation environment. We can't just say, okay, go write some code and then we'll run it, because you can be pretty sure that's not going to work very well. So we've also created a simulation environment where, this graph on the left is the one I just showed, what's actually happening on the buoy. In the simulation world, all the same processes are running on the buoy, but we've replaced the actual controllers and behavior of the buoy with simulation, which is in this, I don't know what color that is, it's sort of orangey color. So that project has been done underneath this DOE funding as a part of this project I'm talking about, and is, well, I should add, the goal here is that the control software, any algorithm written on the buoy, has exactly the same interface. The simulator has the same interface as the buoy. So the control software really shouldn't be able to tell whether it's running on the simulation environment or if it's been moved to the buoy. Of course, there's some things on the buoy which exist on the buoy and not in simulation, like a water temperature sensor that's not simulated or something like that. But for the most part, everything's the same, and that's a critical part of this. Is we're not talking about a simulator that simulates the dynamics of the system. It does that, but it also simulates all the computer infrastructure and interface of the system. So that by the time you get a system running in the simulator, it should be a simple matter of running on buoy, just uploading it over there and sort of hitting go. So, so that simulation environment has been written using Gazebo, which is a simulation environment also supported by Open Robotics, the company that sort of is behind ROS. And really, fundamentally, Gazebo provides a 6 degree of freedom physics simulator for multi-body physics simulator. So that's the rigid body dynamics of a bunch of linked together bodies. And then we've added on top of that particular forcings that represent all the specific components of the MBARI system: the pneumatic spring, the electrohydraulic power takeoff device, the wave body interactions in the free surface hydrodynamics, the tether, the change in the heave cone, that sort of thing. Interestingly, I just want to spend 1 second on this. It says here, lack support for added mass. So Gazebo, along with just about every sort of general purpose robotic simulator that we found, doesn't understand the concept of added mass, which I think this audience might be pretty familiar with. And it's because terrestrial robots are much, much denser than the surrounding fluid air, and it's not a significant forcing. But that was something that needed to be added to Gazebo, and we were, under the funding model we have in collaboration with Open Robotics, able to add that capability to the Gazebo simulator, and that's been released and upstreamed in Gazebo, so it's now a feature of this simulator. So we're hopeful that that makes the Gazebo simulator more suitable for marine robotics and that sort of thing. I think I said this already. While running, the ROS interface that the simulator provides to the user software is exactly the same as the real buoy. But of course, there's additional information like what are the incoming waves. There's other information that's in simulation that we also we don't have a complete job of it quite yet, but make available to the simulation environment for debugging or analysis of the process. The way the Gazebo kind of has this neat. Again, these are videos I'm not going to run because I don't think they'll work very well over Zoom. But when you hit play, the simulator runs and you get a nice little animation of the buoy and the waves and that sort of thing. But also the data is coming across live and can be plotted or stored to a file and plotted later or analyzed later. The simulator runs in real time if you want it, but it also run up to 30 or 40 times faster than real time. So there's no real reason to wait around. So you can hit go. The graphical user interface isn't useful faster than real time because the buoy is just bouncing around like crazy. But it can run, and you can run. It runs fast. Like you can run 10, 20, 30 times faster than real time, depending on a little bit on how fast your computer is and how much fidelity you're looking for in the simulation. So, as I said, the whole goal of this is to enable outside researchers to kind of participate in this project and write some software to deploy on our system. One reason I'm here today is to sort of spread the word a little on that. And of course, any scenario is going to look like simulation first and then on buoy operation. So we're going to probably want to see somebody running pretty successfully in simulation before we let her loose on the buoy. And any buoy operations would be involved. MBARI's personnel would be involved in that. But we are funded for a while longer anyway from DOE to kind of provide that support to people coming into this and participating. And we have a few candidates. We're getting there. I'll talk about it in a second. We're just now releasing all this software officially, so it's just starting to kick off in terms of opening it up to outside users. We are recognized that researchers, other participants might be kind of ROS beginners. So we've really worked hard to make the system approachable and use the simplest solutions possible and not get too crazy on the computer science side of thing. We've provided tutorials and examples. It says good tutorials and examples. We want them to be good tutorials and examples. The proof will be in the pudding. There's probably some little, when more people use them, we'll probably find things that can be clarified. Additionally, you can install the system in a couple different ways, Docker, install from source. And we have a discussion forum that just got launched last week, actually. So it's pretty new, and we're hoping to be as responsive as we can. Again, as we have some Department of Energy funding to support that. So this is where you go if you want to check this out. This website address, this is all GitHub hosted, which has really been pretty great. But this is a screenshot of the entry page of the project. And maybe if Michael Anderson's on the call, I believe he is, maybe you could put that address in the chat in case people want to be able to cut and paste it. That'd be great. But Michael Anderson's a software engineer at MBARI who's, I think, on the call and has participated extensively in developing this work. So anyway, this is the entry point and leads to instruction. But the most important thing on this first page, it says see documentation here. So there is another website that this links to. So you don't need to write down the next one, that kind of has all the documentation, hopefully, that a person would need to use this to install and use this software. So there's some description of the system, how it works, and a lot of specifics here. But again, the most important thing, I think, is this tutorials. There's a list of tutorials that hopefully lead people through from never having done this before to being able to run the simulator and write some code. So it starts with install the system on your system and go from there. It is an Ubuntu Linux based system. So this at the moment does require that you have some facility with a Linux machine. So So the list of tutorials starts with a general installation that can be installed using Docker or from source code. Then how to run the simulator, a number of different examples of getting into increasing complexity, how to look at the output data, adjust parameters, this sort of thing. And then the third section is how do you add control code. So there's some examples here describing the messages and services of ROS2. And then there's example code with sort of GitHub repository templates, which give you the basic starting point. So you could get in there and it's almost, we try to make it as much like your code here. So you write a little piece of code and here come, you're getting in all the telemetry from the buoy, and you are now, your job in life is to tell the system how much force to put on the power takeoff device. So there's a few examples there, and there's bindings for both C++ and Python, depending on your interest. Python's pretty popular, so. And that's very typical of ROS, is to have C++ or Python. So we're not reinventing the wheel there, but just using what's kind of pretty typical in ROS. I will say ROS, there's a little bit of a learning curve. There's a build process, and it's a little complicated to make it all work, which is take a little practice to run through the installations. But we're hopeful that people can come through and do this. And like I said, we've tried to abstract away as much of the complexity as possible. We do have a sort of discussion forum, which just opened up a few days ago, actually. So I made a little welcome message in there, and then somebody asked a question, which we've responded to. And I think we'll try to be as responsive to this as possible, so that if people get involved in this, perhaps people on this call have students that would want to look into this. We're going to, like I said, we do have some funding from Department of Energy to support this. So we're going to try as hard as we can to kind of be on it when people respond or ask questions. So that, before I get to my concluding slide, I want to say that I think that the system's kind of a little ambitious and an interesting chance for us to make the device that we're fielding all the time available. And we're super interested in encouraging people to come use it at any level. I think there's a very sophisticated researcher, could probably do some work here, and we'd love to host the code and put it out on the device, and we'll try to support that. I also think there's probably educational opportunities where people could use this just to learn something about wave energy converters and the marine engineering and marine ocean engineering. So I don't know, I'm not an educator, but I do like the idea anyway of somebody using some of this in a classroom environment. So if anybody on this call is interested in something like that, by all means, let me know. And we'd be happy to talk about how we could make it more approachable for those types of uses, or really any uses. So we're getting to the end of time here, but I want to say something about the people that have worked so hard on this system. This is about 12 years of wave energy development. We don't work on it full time, but we work on it pretty regularly, and we often do long-term deployments. So right now it's out there for the summer. So we're hopefully working on other projects. But it's been an excellent group of engineers to work with. These are MBARI staff: Francois, Scott, Michael, John, Rich, Eric, Dennis, Rob, Jose, and John are at the bottom, plus a number of others. But it's been a pleasure to work on this project with all those people, and we really are grateful for MBARI to give us the chance to do this interesting engineering work. You can see that 3 of my 4 pictures have a picture of the heave cone, which gives you a hint that we're kind of proud of it. And that on the right is Francois in the upper right, and it's also Francois in the lower right. It's one of my favorite pictures of diving in our test tank here at MBARI. Sort of, I don't know, I guess we were looking to see how it looked underwater. So anyway, that's what I have to say, and I'd be happy to take questions or further discussion. And if you do have questions about this or anything else we're doing at MBARI, you can also contact me. I'm easy to find, hamilton@mbari.org.
Awesome. Thank you so much, Andy. That was excellent. We do have a couple of questions in the chat. One of them says, do you think there will be other instruments that will require more power/data in the future that this power could be useful for? Maybe eDNA or something similar?
Yeah, I mean, that's the idea. eDNA is definitely a exciting topic right now. We're doing that at MBARI really as AUV based developments. Not to say it couldn't be put on a buoy. I don't know what the power requirements of those systems are. Probably not tiny because there's a fair amount of computational work. So I think eDNA is a good example. The example that's come up more recently is the DAS systems, distributed acoustic sensing, which are, I'm not an expert in this, but I did go to a workshop, so I can use the words. These are fiber optic sensors that you lay a fiber optic out over some kilometers or tens of kilometers, and these devices blast a laser down there, and by some interferometry magic, they can tell the vibration or movement of the fiber on a meter by meter basis all the way down that fiber. And they're using these in terrestrial locations, and there's companies that build these units that plug into your fiber, and you lay your fiber under your city, and you can get something about the vibrations, and they learn all sorts of interesting things. And it's a seismology project, really. Those systems have been constrained to shore-based systems for two reasons. One is they're kind of 150 watt systems or so, and it's not entirely clear where all that power is going. I mean, there's a laser involved, and there's computation involved. The other constraint is they make a lot of data, like petabytes of data. So we are embarking on a project here at MBARI to investigate how to put those in an underwater environment, because of course, monitoring things like subduction zones off Cascadia or Chile, there's a dearth of data out in the sea. So I think that's sort of a little, ambitious, but that would be a very interesting application of wave energy to power those types of systems. I think a lot of the power requirement is actually computation. There's a remarkable amount of computation just to get the basic data off this sensor. And then in order to really bring it back over a low bandwidth link, like a satellite link or even Starlink or something, in this world, Starlink is like super low bandwidth. The way they get the data back from these sites now is they drive there in their car and they pull the hard drives out. But that's going to be even more computation to do sort of pattern recognition if you're looking for a particular type of earthquake or movement in the seafloor. So I think that's a particularly interesting one that we're kind of keeping an eye on.
Great. Yeah, that seems like it could just be so helpful. Another question was, does MBARI work on thermal gradient power conversion? Or it doesn't,
we don't have any projects, no prejudice. We just don't have any projects in that direction. I think there is, we're aware of some projects like that, but we haven't done anything like that ourselves.
Do you have any, so is it just one of the cytobots that's connected to a wave energy device?
Correct, at the moment, yes.
Is there plans to connect any of the other ones?
No, I mean, the other ones are all based on shore at the moment. I think the Science-y project is kind of leading that a little bit. One thing that they're seeing is this diurnal cycling of the phytoplankton moving up to the surface. We're sampling right at the surface in that device, like right under the buoy. Maybe a couple feet below the surface or 1 foot under the surface. But then they go away at night or daytime. I don't know which way, but they're going to and from the surface, the phytoplankton they're interested in. So I've sort of been saying, hey, we got plenty of power. If you want to stick another one down there, we could strap it to our power takeoff device, which is 2 or 3 meters down, and we could support that from a power and data point of view. But we haven't gotten there. I'm not sure how much enthusiasm there is for that. Or I'm not sure if there's an expensive instrument and you got to buy one and stuff, so slowing it down a little bit.
Sure. And then I know that when we initially spoke back in like November, I think it was, that just a little background maybe you could give on MBARI as far as I believe that you told me that there is like the requirement for collaboration, basically.
No, there's not a requirement, but it's positive. I think that MBARI is funny in that we have sort of most of our budget is coming from our internal sources, but we do have some, maybe 20% of our total project budget comes from external collaborations. And the reason for that really is to allow us the opportunity to do these collaborations, because our funding source doesn't really want us sending money to the University of Washington, for instance. So if I want to work with Chris Bassett on the tidal turbine, which I very much do want to do, then the best way to make that happen is that we collaborate on an external grant request and bring money that way.
Got it. Okay. That's where that came from.
Yep.
Awesome. Does anyone have any other questions? We have about 5 minutes left. someone is interested in you giving a similar presentation at their IEEE chapter.
No, it's better than that. They want the exact one. I'd be happy to do the exact
presentation.
one. Yes. If you want me to make a bunch of changes, we'll have to talk. But yeah, you can contact me. Yeah, I'm not maybe we could talk about exactly who the audience would be, but yeah, I'd be happy to entertain that. And I apologize for anybody who came to my University of Washington APL talk in March, because it's a very similar talk to this one. So.
Well, great. I think it looks like people are really impressed with the work that you're doing and excited to see it moving forward. So, yeah, I think with that, we will close it. So thank you guys so much for joining. Thank you, Andy, giving you a big round of applause virtually. And we will post this onto the UMERC website over the next few days once we get everything processed. So yeah, thanks so much. We really appreciate your time.
Well, thank you so much for having me. I really enjoyed being here. So maybe someday we can do it all in person. Is that a thing that UMERC does? Did you used to have a in-person seminar?
We have our conference, and so but we are definitely open to doing in-person seminars as well. So yeah, if there's ever something that you want to put together, feel free to reach out and we can talk about it.
Okay, great. Well, thank you so much for the effort to put it together.
Awesome. Thanks, everyone.
Bye.
Have a great day.